Hello? Okay. All of you can hear me? Great. Thanks for joining, everyone. My name is Karan Karunakaran, and I'm the CTO for Via Automation. Shami asked me to start talking about horror stories. I wouldn't belabor you on with some technical discussion. Just before I start, I wanted to quickly get a pulse of the audience. How many of you are from semiconductor industry or industrial automation? All right, good. Not too many semiconductors. So I've been in the industry for probably close to 30 years now, before many of the Gen Z is even born. I didn't color my hair just to look old. But let's start with some interesting tidbits about the industry. How many of you heard about this concept called butterfly effect? Great. At least some Gen Zs have started watching fiction movies. So the butterfly effect is the concept where, like, a butterfly flaps its wings in Brazil, and it can start a tornado in Texas, right? So the idea is it's grounded on something called chaos theory, where small effects can lead to bigger consequences far out, right? So why did I say about that? So let's again think about some stories. So imagine you are in a car, okay, and suddenly somebody just jumped in front of you, maybe a Tesla, full self driving car, cut you off and started coming in there. Your car, probably it's not a self driving, it had to do a sudden brake, and the brake didn't work. The next thing is you have the airbags deployed, right? So there is a statistic in US, the 60 to 70% of the failures of airbags is due to a faulty chip. You know that there is a small sensor chip inside airbags. It's all called MEMS. There's a concept called MEMS, which triggers this gyroscopic movement and deploys a sensor, right? Now, I'll tell you another story. In an emergency room, when the baby is born little premature, they put the baby in a NICU, right? So, you know the failure rate of NICUs? It's 20 to 25%. And most of this 20 to 25% failure, it comes from a faulty sensor that's monitoring the baby's pressure or baby's vital health, right? So, there also chip is important. Now, come to our smartphones. We all pay like $1,500 to Apple and get a smartphone or a Samsung phone or whatever, right? And you expect it to work for 5 years because you don't want to be replacing every 3 years or 4 years, right? Sometimes you run into a problem where your phone doesn't perform and it has problems in 2 years. There is a faulty chip, right? So all these have a contributing cause. And that's where semiconductor industry is really important, because if you look at our industry, I've come from semiconductor background, so we make all these chips within clean rooms. When we do process inside semiconductor, any process deviation that happens in the device can contribute to any of these problems. These are all the butterfly effects of semiconductor industry happening. So those are the horror stories if you work in semiconductor industry, right? So the small things that you do and monitor leads to a larger outcome. So what we do at Via Automation is try to reduce all these problems that you may run into, right? So we put AI to make sure the chips that you manufacture in fabs are really performing to the level that it is supposed to perform. So you don't run into a problem when you are braking your car, or you don't have a problem with your smartphone. So that's where we put our AI into the mix. So sorry about that. Let me go back to previous slide. It's going. Let's go back. Let's see if I can go back. Oh, it ended. So, okay, Sharmi, I need your help to get back the slide, but it's coming up. So, what we do is, can you pull the slides back up? So, what we do is we have a platform which is an industrial AI platform. It does multiple things. So, you see all these devices on the walls. So, we actually write software to control these devices. So, what happens in a semiconductor fab? What they have is these things called equipments. So you know all the Silicon Valley is full of semiconductor companies. So we have something called VR control, where we talk to these machines or these devices and make sure a chip manufacturing or the manufacturing process runs smooth. That's one of the software. Then we also have an AI software, which is the Copilot, just like your Microsoft Copilot, where you can ask questions against the tool. These are dumb devices. They're just a bunch of signals coming through, time series data, right? How do you make sense of the time series data? So there are a lot of things involved. So we create models. You're all familiar with all the LLMs and things like. LLMs are a little higher level. They're a different dimension. But when we go into the control system, the dimension is slightly different. It's time series. So we have options to connect to time series data, manipulate the data, control the data. That's where we build our software. So this is part of our software solution. Now again, this is a lightning talk, so it's only 10 minutes. So probably I'll talk about the horror scenarios. So how many of you have done LLM programming or fine tuning? Right. So fine tuning is the cons for others who have not really worked on the LLM. So large language models, what they do, there are two different kinds of memory, right? So even humans, we call it like the book knowledge, what we learn from college or what we learn from our day-to-day experiences. It's called semantic memory, right? That's broad knowledge. If I want to know about like the inside of this control system, I need to go and refer a book and learn about it. That's called semantic memory. But when these devices are in a factory and they are operating under the control of some software, it becomes episodic memory, right? So episodic memory is very important because you may run into things that you may not have seen before. So what need to happen is when you do fine tuning, you do something like um, uh, prompting and adjusting things, right? So the horror story is about a prompt. What I showed you, the Copilot, because it learns about all these manuals, because Beckhoff have a lot of manuals in here, right? So we ingest some of those manuals and try to augment the LLM to be knowledgeable about the control system. Now imagine if in one of the Beckhoff manuals or one of the documentation, the LLM learns that, okay, I can send a specific signal and I can kind of fine tune a particular module here, right? So there is a way for people to do prompt injection, and that can make the whole thing go wrong. We have run into those situations where you can have, because we are working with a expensive output, which is a wafer chip. The wafer has it goes through like close to 2000 processes before it becomes a chip. So if you are not doing the thing properly, you can run into multiple problems. So that's one horror story there when things go wrong. So another one is a very interesting one. So we all know that LLMs hallucinate. So imagine like somebody is troubleshooting a problem and LLM confidently gave you the information that, hey, I know that part number. That part number three, whatever the XX500 is having a problem and you need to reorder the part. It can be just hallucinating, but if you really trust and the LLM to give you that information, it can have a total chaos in your industry, right? So another one is black box anomaly, because we all learn from historical information. This is factory production data. Sometimes you cannot trust the data because every shift is different. People operating in the midnight shift may be fudging data. We don't know yet. So sometimes it can be a black box which happen, right? So another one is again stale historian. So these are all different kind of scenarios where LLMs in an industrial setting can go wrong. So how do we prevent some of these things, right? So this is the way, this is an architecture overview of our platform. So what we look at, and again, this is totally different from the typical software engineering. In a control system or a control environment, we have different people working on the system. You may have process people who are actually creating recipes that need to be run on tools to generate the chips. So there could be agents coming in here, and these are all the application layer. There could be maintenance people, there could be operational people. So those are the solutions that we provide, but the whole key part is where the platform comes in, right? If you are to build your own solutions, you need to look at things like guardrails. So what are the parameters in which this LLM can operate? So the building the guardrails, building observability, those are all things in here. And then you have systems of record. It could be a something like an SAP or something like a Salesforce. So we have to connect to all these things, and this is how we built the whole platform together. And now the last part of the slide is like, how do you bring order into this chaos or this butterfly effect? How do you stop those hallucinating stuff, right? So what we do is we constrain every agent with domain policies. Again, this is not only semiconductor, this is industrial automation. So you go across multiple industries, you'll have different segments. Within oil and gas, you'll be doing something different. You don't want the chamber to open when the pressure is at some level, right? So all those constraints and controls need to be done. We also have something called grounded intelligence. What we do is we have this concept called digital twins. So you build digital twins out of this model. So this box that you see here finally gets abstracted into some kind of a chamber, some kind of a valve, some kind of control, and then the AI knows, okay, this is connected to another device, and this is how it needs to be operating. Then obviously transparent, all these things are there. The whole point is AI, from our experience, from our recovering from the horror stories, AI, it doesn't fail because it's too intelligent. It really fails when it forgets where the truth lies, right? Trust is important. The way we trust a human, you cannot have the same kind of trust in a AI until it can perform to some level of confidence, right? So that's where you minimize these butterfly effects, and that's what we do. Like 10 minutes? Almost there? All right. 2 more minutes? Okay. All right. Maybe I'll skip all this time. These are all the challenges. So this is just an example of how in an factory setting, how different systems come together and play. This is a co-pilot that we built. Again, we talked about the multi-agent interface. It's multimodal. And again, when you build agentic AI for industrial setting is slightly different from other settings. It needs to be explainable. It needs to be grounded on facts. It has to be multimodal. A lot of things around it. And this is how we kind of ground the whole thing. We built something called a digital twin. So this is how an equipment looks like in a factory. This is a semiconductor tool, and then you will have different chambers. So the one of the chamber would be having a device like this that could be controlled by a system like this, right? Then you, as you know, there could be different things like time series data coming in, historical data coming in, manuals coming in. So it's not just pure LLM and you throw in a bunch of LLM and ML and suddenly everything starts working. No, you have to do other things in an industrial setting. You need to be grounded on real facts, and this is the protocols that we need to operate on, right? So that's how we kind of prevent the butterfly effect. All right? Any questions? No, if you look, yeah, maybe let them finish. Great question. So the question is like, why do you need systems like Copilot when you have a highly advanced industry with process controls and fault detection systems, right? Let me ask you a question. Do you know what is the latest technology node in semiconductors when which NVIDIA is operating? NVIDIA chips are made 3 nanometer, right? So how many companies are doing manufacturing at 3 nanometer? Yeah, TSMC, right? And do you know what is their yield rate? Yeah, 3 nanometer chip size. What about the latest AD? So when no, the yield, right? Yield. How many chips are good chips? If you make 100 chips, how many of what is the yield rate? The current yield rate. Totally. So I'll just give you a general thing, right? So at yeah, and it varies from fab to fab also. So the latest fab, which is the TSMC fab in Arizona, they just achieved 92% yield, right? Which is really good. Nobody else has achieved it. In 2 nanometer, which is the other than that, is still 56% yield rate. So when we talk about yield, so assume you have 100 good dice. Dice is where this thing is. So you may get a luck by draw. So you may get that one or two chips which may be defective, and that could be in your phone, right? That's how the yield is influenced. So you can solve the 80% of the problem. The 20% is where the real hard problem fabs are doing. We are working with the fabs to solve that 20% also. How do we increase your yield rate from 56 to 90 when a new nanometer comes in? That's where the Copilot comes in. And to answer your second question, we don't send it to cloud because every fab, it's a closed industry and it's a closely guarded recipe that runs, right? You don't have data going out. So all our systems is in-premise AI. So it has to run in the customer's local environment, and the LLM need to be tuned on customers' data. So that's where we come in. Does it help that question? Yeah, you can have still have fault detection systems and other things which are already there. But what's really happening is there are concepts in semiconductor like advanced packaging, which is happening. And advanced packaging, new processes involve new steps, and that's where you need more AI or more predictability. And that's where the platform comes in. Any other question?
I got tons, but I'll ask you afterwards.
Sorry?
I have tons, but I'll ask you
Oh
afterwards.
yeah, sure. Okay, I think that's all.